as lowering the temperature of an enclosed system by removing the heat from that space and transferring it elsewhere. There are several refrigeration systems, but today we'll be discussing vapor compression refrigeration system, also known as VCRS, which uses refrigerant and undergoes phase changes. This method is most widely used for air conditioning of buildings and automobiles. It is also used for domestic and commercial refrigerators, large-scale warehouses for chilled frozen storage of goods and meats, and hosts for other industrial and commercial services. Some industries also uses this refrigeration system. For example, oil refineries, petrochemical and chemical processing plants, and natural gas processing.
For the problem, a vapor compression refrigeration system with a capacity of 10 tons has superheated refrigerant on 134A vapor entering the compressor at 15 degrees Celsius, 4 bar and exiting at 12 bar. The compression process can be modeled by PV raised to 1.01 equals constant. At the condenser exit, the pressure is 11.6 bar and the temperature is 44 degrees Celsius. The condenser is water-cooled, with water entering at 20 degrees Celsius and leaving at 30 degrees Celsius with a negligible change in pressure. Heat transfer from the outside of the condenser can be neglected. Determine A. The mass flow rate of the refrigerant in kilograms per second. B. The power input and the heat transfer rate of the compressor, each in kilowatts. And C. The coefficient of performance.
For the given, our working fluid will be refrigerant 134A with a molecular weight of 102.03 grams per mole. Refrigeration capacity 10 tons. Temperature entering the compressor 15 degrees Celsius. Pressure entering the compressor 4 bar. Pressure exiting the compressor 12 bar. Pressure at the condenser exit 11.6 bar. Temperature at the condenser exit 44 degrees Celsius. Water initial temperature will be 20 degrees Celsius and water final temperature will be 30 degrees Celsius. The figure shows the temperature entropy diagram for the whole process, wherein process 1 to 2 is an isentropic compression of refrigerant from state 1 to the condenser pressure at state 2. Process 2 to 3 is a heat transfer from the refrigerant as it flows at a constant pressure through the condenser. The refrigerant exits as a liquid at state 3. Process 3 to 4 is a throttling process from state 3 to a two-phase liquid vapor mixture at 4. Process 4 to 1 is a heat transfer to the refrigerant as it flows at constant pressure through the evaporator to complete the cycle.
The next figure shows that 10 tons entered the evaporator, leaving and entering the compressor at 15 degrees Celsius and 4 bar, exiting at 12 bar with the cooling water initially at 20 degrees Celsius and leaving at 30 degrees Celsius. The refrigerant are condensed, leaving as liquid. The liquid refrigerant leave the condenser at 44 degrees Celsius and 11.6 bar. At the expansion valve, the throttling process occurs.
We are required to find A. The mass flow rate of the refrigerant in kilogram per second. B. The power input and the heat transfer rate for the compressor, each in kilowatts. And C. The coefficient of performance. For the equations to be used, it is from the Fundamentals of Engineering Thermodynamics by Michael Moran and Howard Shapiro. For the pressure-volume relationship, we have PV raised to 1.01 equals constant, where P is pressure and V is volume. And for the polytropic Wordsworth equation, we have WC over M equals N over N minus 1 times quantity P2V2 minus P1V1, where WC over M is the rate of power input per unit mass of the refrigerant flowing. And for the reduced mass and energy balance equation, we have Q in equals M times H1 minus H4, where the Q in is the refrigeration capacity, the M is the mass flow rate of the refrigerant, and H1 and H4 is the enthalpy at state 1 and state 4. For heat transfer rate, we have QCV equals negative WC plus M times quantity H2 minus H1, where the QCV is the heat transfer rate and H2 is the enthalpy at state 2. And for the coefficient of performance, we have the beta equals Q in over WC, where the beta is the coefficient of performance.
For the presentation of solution, at state 1, pressure 1 is equal to 4 bar and temperature is equal to 15 degrees Celsius. Using table 1, properties of superheated refrigerant 134A vapor, enthalpy 1, entropy 1, and volume per kilogram are interpolated. Enthalpy 1 is equal to 258.155 kilojoule per kilogram. Entropy 1 is equal to 0.93485 kilojoule per kilogram Kelvin. And for the volume per kilogram, 0.05258 meter cube per kilogram. At state 2, pressure 2 is equal to 12 bar, where the formula to be used is pressure 1 times volume 1 raised to 1.01 is equal to pressure 2 times volume 2 raised to 1.01 to get volume 2. Volume 2 is equal to 0.01772 cubic meter per kilogram. Using the acquired volume per kilogram, enthalpy 2 and entropy 2 are interpolated using table 2, properties of superheated refrigerant 134A vapor. Enthalpy 2 will be equal to 281.3346 kilojoule per kilogram, and for the entropy 2 is equal to 0.9341 kilojoule per kilogram Kelvin. At state 3, temperature 3 is equal to 44 degrees Celsius, having a condition of compressed fluids, and using the values of table 3, properties of saturated refrigerant 134A liquid vapor temperature table, the enthalpy of number 3 is equal to 112.22 kilojoule per kilogram, and the entropy for state 3 is equal to 0.4054 kilojoule per kilogram Kelvin. At state 4, throttling process, the enthalpy at state 4 and enthalpy at state 3 is equal to 112.22 kilojoule per kilogram. Now, let's complete for the compressor work input. Since N is equal to 1.01, where it is polytropic, thus the working equation for this polytropic process is rate of power input per unit mass of refrigerant flowing is equal to N over N minus 1 times the quantity pressure 2 times volume 2 minus pressure 1 times volume 1. Substituting the values, we get 23.432 kilojoule per kilogram. Next is the calculation of mass flow rate, where the conversion of 1 ton is equal to 211 kilojoule per minute, where the refrigeration capacity is equal to the mass flow rate of the refrigerant times the quantity enthalpy at state 1 minus enthalpy at state 4. Substituting the values, we get the mass flow rate of the refrigerant is equal to 0.2410 kilograms per second. The compressor power input is equal to the mass flow rate of the refrigerant times the rate of power input per unit mass of refrigerant flowing. Substituting the values, 5.6471 kilowatts. For the heat transfer rate is equal to negative compressor power input plus the mass flow rate of the refrigerant times the quantity enthalpy at state 2 minus enthalpy at state 1. Substituting the values, we get negative 0.0608 kilowatts. Lastly, the coefficient of performance is equal to the refrigeration capacity over the compressor power input. Substituting the values and converting them, we get 6.2274.
For the final answers, mass flow rate of the refrigerant is equal to 0.2410 kilograms per second. For the compressor power input is equal to 5.6471 kilowatts. For the heat transfer rate is equal to negative 0.0608 kilowatts. And for the coefficient of performance is equal to 6.2274.